Okay, so what we're up to today, everybody, is, as I said yesterday, we're going to start going over kind of the derivatives and integrals of the logarithmic functions and exponential functions and things like that. Okay. But before we begin that, I'm going to start off with a little bit of an exercise. Okay. Kind of keep things simple here. Okay. I wrote up 1 over x squared dx. Okay. I'd asked you to come up with this antiderivative. What would you do?
So it's x to the negative 2.
Okay, bring it up as x to the negative 2. Then what?
Substitute for you.
Although I need to do substitution for this one?
No.
Yeah. Just bring it into derivative.
This is x to the negative 1.
Okay, so we just use our anti-power rule. We get x to the negative first over negative 1 plus c. No problem there, right? Okay. Well, what if I was doing, instead of 1 over x squared, what if I did the integral of just 1 over x? How would I rewrite that?
X to the negative 1.
X to the negative first. Okay. And then, what did you say the antiderivative would come out to be if I followed through with this? X to the 0th over 0 plus c. That's problematic, isn't it? Okay. Especially because, remember, what does the integral ultimately represent? The stuff underneath the curve, right? And what does the graph of 1 over x look like? It looks like that right there. So, are we saying then that this material under here, that distance there, that's undefined? There's clearly stuff there, right?
Yes.
So, what do you think is going on here then? Could this be the actual antiderivative?
C. You have C there.
Well, I've got c there, but if undefined pops up in an equation, the whole thing's undefined.
And you just cross it out and
Doesn't work that way.
Well, we need to do something else.
So,
Guess we can
good,
use logs.
good intuition. There's something else going on here, isn't there? Okay, and that actually brings us to our logarithms. Actually, this is actually a special antiderivative. Okay, so we can just cross all this out because it's flat out incorrect. Okay, instead, the antiderivative of 1 over x dx is a special one. It's equal to the natural log of x plus c. Okay, so ends up that the natural log of x has a special derivative, just like 1 over x has a special integral. So, remembering that these things flip around, what do you think the derivative of the natural log of x is going to be? 1 over x, right? So, because remember, if this is the case here, then if I flip it around, okay, we get the opposite there. Okay, so it turns out, okay, that 1 over x, okay, its antiderivative, its integral, is special. Doesn't behave under the normal rules that we're used to, and instead of just being equal to one specific thing, is equal to the natural log of x. Likewise, the derivative then of logarithms, like natural log of x, are equal to 1 over x, so on and so forth. By the way, if this is the case with this guy right here, do you think then that if x was something more complex, what sort of situation would I end up with? Think of it this way, okay? Let me rephrase the question, okay? If I had, for example, the sine of x squared, and I asked for its derivative, what would I say it is?
cosine of x squared.
Cosine of x squared
Times 2x.
times 2x, okay? It's a chain rule, right? So, if we compare that with our logarithm one we just did, what do you think it's going to do?
natural log of x
1
squared
over
times
x
x.
squared.
Okay,
Just kill that.
1 over x squared times
2x.
2x, good. It also, too, is a chain rule. Okay, and so basically, logarithms, they're chain rules. Okay, and the basic form of them, all right, comes out to be, if we were looking at this kind of symbolically with as we did with all the other functions, the rule for the natural log would be that the derivative with respect to x of the natural log of f of x is equal to the natural log, is equal to 1 over f of x times f prime of x. Okay, so this is then our derivative of the natural log. Okay. Now, do you think this is going to be the case for all logarithms? No, you're shaking your head, Mac. Why is that the case?
That's a good question.
It's a question.
Only log natural.
Only, okay, so, this is the natural log, right? What's its base? E. So, other logarithms, they would have a what?
Base of 10.
A base of 10 or a base of anything other than e, right? Okay, so basically, this trick here, this definition only works for the natural log. If I had a log in a different base, I would quickly run into a problem. Okay, so let's see what happens there. So what happens with different bases? So, again, just for reference, the natural log of x, its derivative is 1 over x. Whoops. What happened there? Oh, there we go. Okay. So, alright. But let's say I did instead the derivative of the log base 10. I would guess that it's going to look something similar to this up here, okay? Because, let's face it, logarithms are pretty much, they all work the same way, don't they? Okay, when it comes down to it. And just because the base is different, doesn't mean that the log is, doesn't mean that the thing should be different, any different, okay? But again, it's not going to be exactly the same, right? And the reason for that is because we've changed the base. So what we're going to be up to here, okay, is we got to find some way to make it work, to make it be like 1 over x dx. And it turns out there's a way to do so, okay? What you're going to end up doing here is basically you're going to make this thing in terms of the natural log of x. Okay. Now, how would I normally do that? Anybody remember? What property do I have of logarithms that lets me change the base of something?
Change base formula.
Change a base formula. What does that look like, Tate?
But what the base is, I forgot.
It's log of x over log of 10.
Log of x over log of 10. Good. But since we don't want it to be log, we want it to be ln. When we change the base formula, does it matter? No. Good. So what I'm going to start off doing is, instead of doing it directly like this, I'm going to use that change of base formula. And I'm going to rewrite this as the derivative with respect to x of the natural log of x over the natural log of 10. Okay? What happens with natural log of 10 there? What is that, ultimately? It's just a what?
Just a constant.
It's just a constant number, right? So I can actually rewrite this whole thing to be the derivative with respect to x of 1 over the natural log of 10 times the natural log of x. And don't we know the derivative of the natural log of x? Yeah, it's 1 over x, right? So this whole thing then should become out, and constants stay where they are.
What's the point in splitting it up like that, like you did?
Of doing it like I did right there.
Well, why'd you split, after you changed the base, why did you split it up right there?
Oh, just to make it a little easier for you all to see that that was a constant. Also, too, another reason I did it that way is because by pulling out that 1 over natural log of 10 like I did, I can clearly see now that all I'm left with is really just the natural log of x there. That's the only function part of this, if you will. And so the derivative of the natural log of x is 1 over x. We had just determined that earlier. Okay. But anyway, anytime you have a base that's different than the natural log, this is what you end up doing. Okay? And so the rule for that, for different bases, okay, let's add that on there. Okay, so the rule for different bases is the following. Basically, you do the derivative with respect to x of the log base a of f of x is going to be equal to 1 over f of x times the natural log of one of the bases times f prime of x. Okay, like so. So it gets a little bit more drawn out, but it's still, you're still able to do it just fine. Okay. So basically, anytime you've got, anytime you have a logarithm that's a different base than what you're used to, or that's a different base than e, basically, to handle this derivative, you just add in a natural log of whatever base that is in the denominator, and you're done. Okay. So it comes out nicely. Either
So
way,
you always
just like
use
that.
the natural log when you're doing change of base.
Exactly. You're always going to be using the natural log. And not only with the change of base, but anytime you do a derivative of logarithms, it always comes back to that natural log. Turns out Euler's number is really important, isn't it? E, yep. It always comes back to E. Okay, so to kind of rehash here with the logs, okay, basically we start off with the definition here, that the integral of 1 over x dx is equal to natural log of x plus c. So the derivative of the natural log of x is 1 over x, okay? And then we get 2 new derivative rules. The first one being that the derivative of the natural log of f of x is 1 over f of x times f prime of x, okay? And then our next one here is that the derivative of the log base a of f of x is equal to 1 over f of x times log of ln of a, excuse me, messing that up, times f prime of x. Okay, and that's pretty much everything there is for the logarithms. Okay, yeah.
You derived the bottom two. Are we just supposed to take the top one on faith?
The top one. Okay, so why is the 1 over x equal to the natural log of x? Short answer is yes. You want to take it on faith right now. The longer definition of it all comes back to doing a Riemann sum of basically the natural log. Okay, so if you remember, to explain this one fully. Okay, And I typically don't go over this because it just takes way too long to go
Ben,
over.
don't do it. Don't do it just to satisfy my curiosity.
Okay.
Do what you gotta do.
Because, yes, if this was a calc theory class, we'd all be doing that, and it's not hard. Basically, you just do a Riemann sum of 1 over x, and you see quite quickly, as you put in the values, they're equal to the natural log of x.
Yeah.
And so if they're equal, they have to be the same thing, okay? According to the formula here. There is a reason for that. All right, any questions though about the rest of logarithms? Okay, so that's really it. So are logarithms all that difficult? No. If I'm doing a derivative of a logarithm, it's just a chain rule. And the only time they're gonna, well, not the only time, but really when I'm looking at the integral, it answers the question of what happens with the integral of 1 over x. Okay, so it all works out nicely that way. All right, let's see here. Let's go ahead and move forward then. Okay, that covers logarithms. Okay, what's the other big type of transcendental function what we know of? Mentioned it yesterday. So what's the opposite of a log? Exponentials. Okay, well, what happens with those? Okay, again, we started off with the natural log, so we're going to start off with just functions involving e here. Okay. What happens? And this one's really strange. What happens with exponentials like e to the x? Okay. To ask again, who remembers what e to the x actually is?
It's just an exponential function.
It's an exponential function, but how do I get it?
It's an
How do I get the number e, basically?
Isn't it a value?
It's a
Isn't it
number,
like
it's like 2.4.
Okay, so we know it's 2.71828 and change after that. But it ultimately came from what? I know this is pulling way back from pre-calc.
It's a ratio, right?
Okay, you can think of it kind of like ratio, but not quite.
It's a
Some
nature,
like
something in
perfect
nature.
thing for logs.
Something from a circle.
Something from a circle, no.
It's a
The
nature.
perfect
It's a
log.
growth, it's like a growth thing,
Okay, it's a growth function, right? What type of growth specifically?
population.
Okay, so population growth,
Exponential.
exponential growth, or specifically compound growth, okay? So remember like compound interest formula from last year, and those sorts of things, and how we can use that to come up with E? Remember, E is equal to, it's actually not no approximation there, it is equal to the limit as n goes to infinity of 1 plus 1 over n to the nth power. That's what E is equal to, okay? So e to the x would be equal to the limit as n goes to infinity of 1 plus 1 over n to the nth
Where are you getting in?
to the x.
It's just the
It's
x.
just part of the limit, yeah. Okay. This is the definition of, remember, this goes back to the definition of what E is. Okay. So this ends up being excuse me, what E is equal to. Okay. Now, if you're like me, do you really want to try to do the derivative of that right there? No. In fact, could I do the derivative of that easily? No. I'd be using the definition of the derivative, and we'd be popping that in, and we'd be working with it and stuff like that. And we would quickly end up with this big mess of numbers that we could fully work out, but it would just take us a very, very long time to fully figure out. So there's got to be a better way, okay, of handling this. And it turns out there is, okay? It all goes back to a property of exponents. Or not property of exponents, sorry, property of logarithms. okay? What happens when I do the natural log of e? What would I get?
E.
Nope,
Is there one?
it is 1.
Oh.
Okay. The natural log of e. Remember, the log base a of a, or natural log of e, or anything like that, always comes out to be 1. Okay? So that means then, the natural log of e to the x should be equal to just x, correct? Okay. So, from that then, if I decide to do, if I decide to take the derivative of this, okay, what I'm going to be doing here is I'll be doing the derivative with respect to x of the natural log of e to the x, like so. We already know what that should come out to be, okay? It should come out to be 1 over e to the x, right? Times whatever the derivative with respect to x is of e to the x, correct? But we know this whole thing needs to be equal to 1, correct? Why would it need to be equal to 1?
Because
Because what's this equal to?
Because
That's equal to x, and the derivative of x is 1, right? So kind of as a reminder here, this was x, and the derivative of x is equal to 1. So that means then, what I've got starting off here is I've got the derivative with respect to e to the x, okay, times 1 over e to the x is equal to 1. That's what that upper equation gives me. Well, I want just the derivative of e to the x, right? That's what I'm trying to figure out there. Well, how do I get that by itself? What can I do to both sides of the equation?
multiply by
E to
E to
the
the x.
E to the x. So if I do that then, I would get that the derivative with respect to x of e to the x is equal to 1 times e to the x, which is 1 e to the x.
But can you explain why that's equal 1 again?
Okay, goes back to right up here. Teddy, remember, we started off natural log of e equal to 1. So the natural log of e to the x is equal to x, right?
Yeah.
What we're going to do here is to figure out what the derivative of e to the x is. Instead of trying to tackle that, we're going to take the derivative of the natural log of e to the x, okay? Which remember, natural log of e to the x is equal to x, so it's equal to 1 ultimately, okay? Any problems there?
Wait, say that again?
Okay. Natural log of e to the x is equal to x, right?
Yeah.
And the derivative of x is 1.
Yeah.
Okay. So the derivative of the natural log of e to the x must also be equal to 1. Okay, because again, it's all, okay. And so what we're basically doing here is to figure out how e to the x works as far as its derivative is concerned, is we start just basically manipulating this equation right here, which is exactly what we did right there. And we end up, when we clean that up, we end up getting this right here, which then comes out to show that the derivative of e to the x ends up just equaling e to the x. So, basically what I'm getting at here is, the derivative of e to the x is e to the x. It's its own derivative. Okay? It ends up being this really kind of funny thing that happens in calculus. Okay? The derivative of e to the x is e to the x. So if I'm basically, what that means is, if I'm looking at the slope of the function f of x equals e to the x, at any point, the slope is equal to e to the x at that point.
No, that's what I was, the slope is equal to the value of the function.
Yep.
At every point.
Pretty good.
Ends up being, and that's again why e to the x is called the natural exponential. Okay. Again, it's part of just that ingrained kind of cheat code that's in the universe when it comes to these sort of growth systems. That's why e ends up being such an important number. So that gives us two rules, by the way, for e to the x. Okay. So my first rule is that the derivative of e to the x is e to the x. Okay, we saw why that's the case. Okay. Now, what does that then mean the integral of e to the x must be?
Must be derivative of ln
Let's be e to the x.
Must also be e to the x. Good. And you're absolutely right. It would be the derivative of ln e to the x, because that's equal to e to the x. So, so it ends up also, okay. Because if e to the x is its own derivative, then e to the x also has to be its own antiderivative. Okay, and so those are your two formulas for e to the x. I can actually come up here and add a third one, because what do you think is going to happen if I don't have it simply be x up there? If I do a derivative with respect to x, if it's like e to the f of x, what do you think I'm going to get? E to the f of x times f prime of x. Okay, good. Comes out to be e to the f of x times f prime of x. Again, it's a chain rule, isn't it?
But when you do the antiderivative of e to the x dx, why didn't you add a exponent? When you did number 2, why didn't you actually do the antiderivative of e to the x? Wouldn't it be e to the x plus 1 over 1 plus c?
Plus 1 over 1 plus c. What's 1 over 1?
1.
1. So you're basically saying, would it be e to the x times 1 over 1?
Plus 1.
Okay.
But then you add an exponent, right? When you do the antiderivative.
If it's a regular, yes, you add an exponent if it's a regular derivative, if it's for the antiderivative of a polynomial. Okay? So remember, that means it's in the form of x raised to the n. That's when you do the antiderivative rule like that. Okay? But in this case here, we don't have this. This is not a polynomial. It's an exponential. Okay? Is that clear?
Mm-hmm.
It's the same reason why when I do the antiderivative of the sine of x, or the cosine of x, or something like that, I don't also do the anti-power rule to x there. Okay? It's simply because it's not that type of function. Right? But this gives us our rules for e to the x. Okay? Any questions here? Nope. All right. Well, that's great for e to the x, but is e to the x the only type of exponential function? No. What if I had something like instead, like 2 to the x, or 10 to the x, or something like that? What on earth is going to happen there? Okay. Well, again, you're going to, excuse me, you're going to change things so that way they're in terms of, again, things that we can handle. Okay. So let's look at an example of that. Okay. So basically, exponentials other than e to the x. Okay? So the first one we're going to deal with here, let's just look at an example one of, let's keep it simple, we'll do 2 to the x. Okay? And what I want to know is, I want to know what the derivative with respect to x is of 2 to the x is equal to. Okay? Now, if you remember when I did things with the logs, okay, with a logarithm, when it wasn't in terms of the natural log, what did I do?
Converted to the natural log.
I rewrote it in terms of the natural log, right?
Right.
Okay. So, what do you think I'm going to have to do to 2 to the x?
Convert it to e.
Convert it to e. Rewrite it in terms of e. Okay? And, again, pulling out from pre-cal, from over a year ago, 2 to the x, rewriting it in terms of e, it becomes e times the natural log, or e to the natural log of 2 to the x like so. Okay? And again, this all goes back to properties of logarithms and exponentials, okay? Remember, for the same reason why if I do ln of e, I get 1, if I do e to the ln, I get 1 as well. They cancel each other out, okay? So I'm not doing anything different here. E to the ln would be 2, okay? Or e to the ln of 2 is just 2, and I'm being raised to the x, okay? So what does that mean I can rewrite this down here as? Could I just rewrite it as this right there?
Yes.
Absolutely. So let's go ahead and do that. Go away. Okay. Okay. But what do we know about the e to the natural log of what do we know about the derivative of e? What's it come out to be?
E to the x.
It's the same thing again. It's to repeat the same thing. The only difference here is though
Chain rule.
is I'm doing a chain rule because I've got this up here. So if I wrote this out fully, this would come out to be e to the natural log of 2 times x, all times by the derivative of the natural log of 2x, which is just what? Natural log of 2 is a constant, okay?
0.
So it's just derivative of x, which is 1, times natural log of 2. So it would just be natural log of 2, right?
Well, hold on. What?
Okay. I've lost you, okay. Let's take a step back here. Maybe it
I
will
missed
help.
that chain rule part.
Okay. Okay, so we know that's that right there, right? And then to fully do this derivative, we're going to multiply it by the derivative, here I'll write it out this way, of the natural log of 2 times x, right?
Yeah.
Well, what's the natural log of 2 again? It's just a what?
Constant.
It's a constant, so it's like, it's roughly equal to about 0.8.
So if you're taking the derivative of the constant and then 0?
Well, it's not just the derivative of constant, what's also there?
The x, oh, I see. All right.
X, and what's the derivative of x? It's 1, so it's 1 times the constant. It's a standard power rule.
So 1 time, yeah.
Okay, so it would be 1 times what was in front of it. It's the same reason why if I had like 3x and asked you for its derivative, what's its derivative?
3.
3? Well, ln of 2, if it helps, as a decimal, like I said, it's equal to about 0.8. So it'd be 0.8x. What does that come out to be? Just 0.8, right? Alright, good.
Why is ln 2.8?
Oh, the natural log, do it in your calculator.
Oh.
It equals about 0.8. Somewhere around there, it might be 0.9. I don't know it off the top of my head exactly. Because I mean, yeah, it's just a standard logarithm. But this is how this comes out here. And so we would get here ln e to the ln of 2 times x times the ln of 2 when I did all that derivative out, okay? Well, what does this, what's that equal to? Wasn't that the relationship between those two?
Yes. So it's just 2x.
So it's equal to 2x, so I can rewrite this whole thing then as 2 to the x times the natural log of 2. So look what happened there. Same thing that happened with logarithms is that to basically I end up with a natural log added to it to kind of account for the fact that it wasn't in terms of e to beforehand. Okay. So again, what that means is the rules for exponentials other than e to the x, the rule for it comes out to be that if I do the derivative with respect to x of any, excuse me, any constant a to the x power is equal to a to the x times the natural log of a. Okay? And likewise, again, it's a chain rule. So if I wrote it a to the f of x, it would be a to the f of x times f prime times the natural log of a times f prime of x. Okay? They always work out the same way. Okay? All right. Any questions there? No, okay. So that means we've done kind of a lot of different properties here today. I've kind of thrown a lot at you. These are the derivatives here. What do you think is going to happen if I did the antiderivative of a to the x dx? Okay. So again, if I did the last one,
dx.
antiderivative of a to the x dx. Well,
So it'd be e to the ln.
okay, so it'd be a to the x again, right? Just like it would be before, but we'd have to add an ln, wouldn't we? Okay, so this would come out a to the x, but this time because we're doing an integral, instead of multiplying it, we're going to divide it. Okay. Well, remember the antiderivative is what? It's the opposite of the derivative. So if a derivative I multiply, for an antiderivative I must divide. There you go. And again, too, think of it this way. The whole idea with an antiderivative is if I take the derivative of it, I should get back what I started. If I take the derivative of this, I would end up with just a to the x again. Okay? So this kind of is the rule for okay. All right. So that's a lot today, isn't it? Okay. But notice how they're not. It's just a matter of knowing a bunch of formulas, right? Ultimately, like, you don't actually need to derive these every single time you do them, do you? You just need to know what the basic formula is. And are those formulas all that difficult? I mean, it's not that difficult to use that, is it? It's just a matter of popping in the numbers, okay? It's kind of the same way with sine and cosine. It's going to just end up falling down to a matter of just remembering what those derivatives are, okay? So when it comes to doing like it on a AP test or something like that, you want to make sure you've got these formulas memorized. And again, because we're all about getting ready for that AP now, if you notice, page 378, where that box was that you had to memorize for the quiz, numbers 9 through 12 were all the rules I had written up today. The ones I told you didn't need to know, well, now you know them. Okay? And the same thing happens on the other page, the one for integrals. They're all there as well. Okay? Everyone got that? All right. So, you've got homework tonight. It's just going to be on the natural logs first. Okay? Because I want you guys to work on that tomorrow, tomorrow, because we have classes on it. We're going to be going over that, just that assignment, make sure you got it down. Okay? And stuff like that. Yeah.
I won't be here on Saturday.
Okay. Just still do the homework, obviously. Just follow along. There'll be a video.
All right.
Sure. So, all right. Okay, everybody. See you later.